Hello, everyone. For the last two classes of the semester now, we're going to talk about something that we haven't discussed before during the semester, and that is the rates of chemical reactions, or what's referred to as chemical kinetics. Until now, what we've discussed, particularly in the context of thermodynamics, has been essentially the initial and final states of a reaction system. Purple regions here, which may be called the domain of thermodynamics. What we've not talked about is how we get from the reactants to the products. How long does it take? What affects those reaction rates? This may be referred to as the domain of kinetics, and that's the topic that we're going to be discussing now for the next two classes of the semester. Kinetics are best described for reactions by what are referred to as kinetic rate laws. And we're going to say more about those in the next lecture. But for now, we can simply recognize that the reaction rate of almost any chemical reaction depends on the pressure of the reactants, if they're gases, or the concentrations, if they're species that are in solution. And that the overall reaction rate can be modeled by what's referred to as a rate law, which is this expression here in red. I'm not going to say anything more about that now because the next lecture will go into that in much more detail. But the general observation is that, and we're going to see several examples of that in today's class, is that the reaction rate for almost all chemical reactions depends on the pressure and the concentration for a very simple reason. And that is because when there are an initial amount of gases or liquids or whatever the reactants may be, they react by colliding with each other, either in the gas phase or in solution, in the liquid phase. And the more of them there are to collide, the faster will be the reaction rate. As the reaction proceeds and the amount or concentration of reactant decreases, there are fewer collisions that can lead to reaction. And so naturally the reaction slows down. And that's what we're going to see in today's class when I show you several examples that illustrate that. Now, reaction rates, as we'll see a little bit later here, can be classified as three different types. One is called the initial reaction rate, which is self-explanatory. It's the rate of the reaction at the very beginning. Another one is called the instantaneous reaction rate. And a third is called the average. And we'll see the difference among these three as we look at several examples now today. And we'll discuss what their significance is and how they're related to each other and so on. Here is an example of a typical chemical reaction. It involves ethyl chloride, C2H5Cl, reacting to form ethylene and hydrogen chloride. All of these are in the gas phase if it's at room temperature, for example, or higher. And so the way we're going to look at it for all of these is that the initial concentration, call it C sub 0, in this case it's 15 millimoles per liter is the initial concentration of the ethyl chloride. And as the reaction proceeds to any point, there will be X amount of the ethyl chloride that is reacted away and X of each of the two products that are formed. And the reason is because they're in a 1-to-1 ratio. So this is typical of what we used to set up as rice tables for equilibrium calculations. Now what's shown here are two plots. One, the green one, refers to the concentration, not the rate, the concentration of the ethyl chloride reactant. As you can see, it decreases with time as you'd expect as it reacts away. And the blue line refers to the concentration or amount of both the ethylene and hydrogen chloride. The same line refers to both of them because they're both in a 1-to-1 ratio, and so they're both formed at exactly the same rate. Now, if we look here at the reaction in its early stages, the reaction time unit is seconds here. So the reaction is proceeding in a matter of seconds, 2 minutes, 4 minutes, and so on. And so the concentration of the reactant decreases with time. Here's that initial concentration of C0, which is 15 or slightly higher. So if we look at some particular time interval, let's say between 15 and 30 seconds, what's shown down here, all right? the concentration amount of ethyl chloride decreases from this value to this value, whatever they are. And that is the change in concentration. It's less than zero because it's reacting away. It's a negative amount. The same interval, time interval, 15 to 30 seconds, can be referred to on the product curve for the ethylene and the hydrogen chloride. And of course, the increase in concentration, which is now greater than zero, has to be exactly the same as the decrease in concentration of the reactant, because the ethylene and hydrogen chloride are in a 1-to-1 ratio with the ethyl chloride reactant. Now, as the reaction proceeds farther and farther, when we get to this interval between 120 and 135, the same 15-second interval, you can see by this little arrow here that the decrease in concentration of the ethyl chloride in that same 15-second time interval is less than it was for the earlier 15-second time interval. And this simply reflects the fact, as we've said before, that as the reaction proceeds, it gets slower and slower. Fewer and fewer moles or molecules of reactant are converted per unit time as the reaction goes on. Given enough time, as you can see by these curves, given enough time, the reaction will eventually reach equilibrium. In this particular case, the equilibrium is virtually to completion. And so you can see that after 400 or so seconds, the ethyl chloride has essentially disappeared, and the same amount, 15 millimoles per liter, of both ethylene and hydrogen chloride have formed, which they must according to the stoichiometry. Now, if we look at some tabulation of that same data for that same reaction, ethyl chloride going to ethylene plus HCl, and this is at 530 degrees, which of course means that everything is in the gas phase. Here is a tabulation of the time intervals, which are in 15-second intervals until about 180. After that, it's in 60-second time intervals. Here's the concentrations, the measured concentration. These are experimental data. These are the measured concentrations of the ethyl chloride that remain after each of these times. And you can see that the measured amount is getting smaller and smaller, as you'd expect. It's reacting away. This is the concentration in this column, the HCl, and also of the ethyl chloride. You can pick either one because they have to be the same amounts. And what's shown here is the HCl concentration. And of course, the concentration of the HCl and the ethylene are increasing with time. And because of the stoichiometry, the decrease in concentration of the reactant is exactly the same as the increase in concentration of product, which it must be because of the stoichiometry of the reaction. So if you look at a particular interval that we did before, between 15 and 30 seconds, that was this interval right here, and where we looked at that change, right? If you look at that same interval between 15 and 30 seconds, the decrease in ethyl chloride from 1279 to 1079, which is 2 millimoles per liter, is virtually exactly the same as the increase in concentration of the HCl. Now, if you take that decrease in concentration of the reactant and divide it by the 15 seconds of the interval between 15 and 30, you essentially get the number of millimoles per second of ethyl chloride that is reacting away. And that turns out to be minus 0.133. The minus is because the concentration is decreasing. And as the reaction proceeds to longer and longer times, right, the concentration of the reactant is going down, the concentration of the products is going up. But if you look at each of these separate intervals here and calculate how fast it's going down, the interval between 15 and 30 seconds had a decrease of 0.133 millimoles per liter per second, whereas between 45 and 60 seconds, it's 0.095. Between 75 and 90 seconds, it's 0.068, and so on. The reaction rate is slowing down, and that's exactly one of the features of most chemical reactions. Of course, the amounts of or concentrations of reactant are decreasing and of products are increasing, but the rate at which they're doing that per unit time is getting slower and slower. And that's characteristic of most chemical reactions, as we'll see when we quantify this. Here's another example. This is for the reaction of what's called T-butyl bromide. You'll learn more about that, what that is, when you take organic chemistry next year. The reaction of T-butyl bromide with water to produce T-butyl alcohol. And it's a fairly straightforward reaction, but it's the same principle. Here, there is a series of time intervals. In this case, they're in minutes, 9 minutes per interval here. This is the initial concentration of the T-butyl bromide, 0.1056 moles per liter this time. And after 9 minutes, it's gone down to 0.0951. Again, if you take that interval of 9 minutes and divide it by the concentrations, if you take these two concentrations, the difference between them, and divide it by the 9-minute interval, you'll see that the change in T-butyl bromide concentration per unit time is 1.17 times 10 to the minus 3 moles per liter per minute in this case. And again, with increasing time, the concentration of the reactant is decreasing. But if you look at each of these intervals here and determine how much remains of the initial concentration and what the interval, the amounts that change over the interval of however many minutes it is, you'll see that the reaction rate is slowing down. It's getting slower and slower. In this case, it starts out early on in the reaction at 1.17 times 10 to the minus 3. And after about 105 minutes, it's down to about 5 times 10 to the minus 4. So the data plotted looked like this. All right, here's that reaction. This is the T-butyl bromide plus water going to form T-butyl alcohol and HBr. The R is been cut off here, but that's what that is. Now, the reaction rate, if you look at all of these tabulated numbers here for the change in concentration per unit time getting smaller and smaller, that's what this green line is that I plotted on top of the same graph with the data themselves. The rate is the highest at the beginning, which is always the case, as we'll see. And with increasing time, of course, the concentration is going down of the reactant, but so is the rate at which it's disappearing. That's the green line here, right? And so we can determine reaction rates, as we'll see in a few minutes, in different ways. But what I've drawn in on this one is this red dashed line here, which is intended to be the tangent to the black line that shows the T-butyl bromide concentration. It's the tangent to it at time 0, which is always where the reaction rate is the highest. The reaction rate, as we see here, and what we'll see later on as well, decreases with increasing time. And so the slope of this tangent essentially reflects the reaction rate. It reflects that the rate that is observed at the smallest possible time, which is at time 0. Now, that has to be the same with the opposite sign as the reaction rate at time 0 for the product that's forming, the T-butyl alcohol here, all right? And so what it means is that these two slopes, these two red dashed lines that I've drawn in here, have to have numerically the same value with opposite signs. The slope of the concentration of reactant disappearing, of course, is negative, and the slope of the product that's appearing has to be positive, but the numerical value is the same. And I measure it to be 1.18 times 10 to the minus 3 moles per liter per minute. Now, as the reaction proceeds, by the time you get to down at 120 minutes, for example, the reaction rate now is about 3.5 times 10 to the minus 4, or about 0.35 times 10 to the minus 3. So the reaction is slowed by a factor of about 3 after 120 minutes. And again, this is typical behavior for most chemical reactions. Concentrations of reactants decrease with time, concentrations of products increase, of course, but the rate at which they do that decrease with time, with the fastest rate being at the very beginning, when the concentrations are the highest. Here's another example of another reaction with different stoichiometry this time. This is the decomposition of N2O5 in the gas phase to 2 NO2s and 1/2 O2. So now the stoichiometry is 1 to 2 to 1/2. Nevertheless, the connection between the various reactant and products has to be given by that stoichiometry. So these black points here, these are data points that were collected for a period of time. In this case, it's in seconds again, but a much longer interval of seconds, as you can see, compared to that first one we looked at. And so at the tangent that is drawn to the curve at the very beginning is supposed to be crossing this data point, this red data point here. That tangent there turns out to be 5.4 times 10 to the minus 4 moles per liter per second. And again, at a longer time, in this case, about where this red point is here, is about 1300 seconds. At 1300 seconds, now the slope at that point is only 2.7 times 10 to the minus 4. So the reaction rate has slowed to 1/2 its initial value after about 1300 seconds. And again, this is typical behavior for most reactions. The difference among the reactions are, of course, how fast it goes down and what the stoichiometries are and several other factors that we'll talk about next time. Here's another figure that shows several things that shows the difference in these various kinds of reaction rates that I talked about. This is the reaction of NO2 plus CO going to NO plus CO2, all in the gas phase. And so the stoichiometry is particularly simple. It's 1 mole of NO2 and 1 mole of CO go to 1 mole of NO and 1 mole of CO2. So the stoichiometry is 1 to 1 to 1 to 1 all the way across. So the initial reaction, the concentration, or in this case, the concentration of the NO, it could also be the concentration of the CO2 because they're in a 1 to 1 ratio here. Concentration of the NO, moles per liter, is shown by this blue curve, right? And of course, as a product, it's increasing with time, as we've seen for the other two reactions we looked at. And so the slope of the tangent to that curve at time 0, which I tried to draw in here as best I could by eye, the slope of it turns out to be 4.7 times 10 to the minus 4 moles per liter per second. That is the fastest rate that the reaction will exhibit, because as the reaction proceeds in time, the rate of reaction slows down. And so what you'll find is that this curve, this line curves. The only way that wouldn't happen is if this were a straight line and then the reaction rate is staying the same, but that never happens for almost all chemical reactions. So the initial rate then is 4.7 times 10 to the minus 4. The rate at, I should try to see this a little bit better here, all right. The rate at 150 seconds, which is down here, is where this red tangent is drawn to the blue curve, right? And it has a smaller slope, of course, than the one that occurred at time 0, or virtually time 0. And the numbers that are shown on here simply reflect the endpoints of that red tangent, so that it goes from 0.0249 moles per liter for concentration at 100 seconds up to 0.0326 moles per liter at the highest, which was 200. And so that's where these two numbers here, if you take the difference between those two, divide by the interval, which was 200 minus 100 second, right? And the slope of that line turns out to be 7.7 times 10 to the minus 5, or with the same exponent, 0.77 times 10 to the minus 4. So it's approximately 6 times slower at 150 seconds than it was at the beginning of the reaction. Again, typical behavior for most chemical reactions. Now, a third kind of rate that can be described for most chemical reactions is what's called the average rate. The average rate, as the name implies, is the average rate that the reaction has over a particular time interval. In this case, it starts at 50 seconds and it goes to 150 seconds. So again, it's a 100-second time interval, but instead of drawing a tangent at any point along that interval, you simply draw a line connecting those two data points and take the slope of it, okay? But of course, if we drew tangents from this point to this point, the tangent would be gradually getting a smaller and smaller slope. So it would look like this red one here compared to this initial one here. But in this case, the average is simply the difference between the two endpoints of this average line here, which was from 0.016 moles per liter at the beginning of that time interval to 0.0288 at the end of it, which is another 100-second time interval. And that, taking the difference between those two and dividing by the 100-second interval, is 1.28 times 10 to the minus 4. So in that interval, it is apparent that the overall reaction rate over this entire 100-second interval is 1.28, which is slower than the initial rate, but faster than it is at some particular point, not an average, but a tangent at some particular data point later on. So as you might imagine, this average rate is less useful than either the initial rate or the instantaneous rate that occurs at some particular point, because it averages over this long time interval. The way the average rate can become more useful is to average over smaller and smaller time intervals. In essence, the initial reaction rate is also an instantaneous rate at time 0. The average rate, if it was done over a sufficiently small time interval, becomes more and more relevant, if you will. If I took the interval instead of from here all the way up to here, if I did it from here to approximately here, now that tangent will be, or that average rate would be very, very similar to the tangent drawn at the midpoint of that interval. So it's for that reason that the average rate is normally used only for getting a quick idea of the speed of a reaction during a particular time period. It's not as useful as the initial rate or the instantaneous rate at some later time. Now, there's one more figure here that I admit it's a very busy figure, but I used it because it shows several things all coming together, so to speak. This is more plots of the same information we've just been looking at, the concentrations of reactants and products changing with time. This reaction is NO2 going to NO plus 1/2 O2. So the stoichiometry of the reaction is fairly simple. The NO2 and NO are in a 1-to-1 ratio, and the NO2 and O2 are in a 1-to-1/2 ratio. The reaction that's shown here, or the data that are shown, are for the reaction occurring at 300 degrees C, which you can see up here. Now, if you look up in a table, the delta H for the reaction and the delta G at 25 degrees, because that's how the data is normally tabulated, it's not as meaningful, and I didn't have available the data at 300 degrees, the delta H and the delta G, but the reaction at 25 degrees is endothermic. It's plus 57 kilojoules per mole for the delta H. And the delta G is also positive, it's plus 35. So at 25 degrees, this reaction would not be the spontaneous direction, because the positive delta G means that the equilibrium constant is less than 1. However, because it's an endothermic reaction, as we know from our thermodynamic studies earlier in the semester, because it's an endothermic reaction, it means that the endothermicity and the delta G get less and less positive as the temperature goes up. So by the time you get to 300 degrees, which you can't tell from these data, but by the time you get to 300, the delta H and the delta G are both negative now. And so the reaction is spontaneous in the forward direction. The exact values for the delta H and the delta G at 300 I don't have, but you know that because it's endothermic, reaction becomes more favorable with increasing temperature, just as an exothermic reaction becomes less favorable with increasing temperature. So if we look now at these curves and show the relationship between them and what the significance is, the green curve represents the concentration of the NO2 reactant. And of course, it's going down with time, as we've already seen for previous reactions. The blue curve is the concentration of the NO product, and the red curve is the concentration of the O2 product. And of course, they both increase with increasing time of reaction, as we've seen before. But now we can draw some important relationships between these various curves and the concentrations they represent. The initial reaction rate, and I've drawn in again a tangent right here, this black line that you can hardly see. And for the NO product, I drew in another one for the initial instantaneous reaction rate at time 0, and that's this black line right here. Now it has, the slope of that line is 4.5 times 10 to the minus 5 moles per liter per second. The times are given here in seconds. Now, there's not a value given for the initial rate for the NO2 disappearing. And the reason why it's not necessary is because the rate of disappearance of the NO2 has to be the same numerically as the rate of appearance of the NO product, simply with opposite signs to the slope. And so the rate of disappearance of the NO2 also has to be 4.5 times 10 to the minus 5 moles per liter per second. So that's the relationship between those two. Now, an initial rate for the appearance of O2 is also not given, but again, it's not necessary because we know the rate of appearance of the NO product. We know that the NO and the O2 have to be in a 1 to 1/2 ratio, so it must mean that the initial rate of appearance of the O2 must be half of the rate of appearance of NO, or 2.25 times 10 to the minus 5 moles per liter per second. Now, as the reaction proceeds, as we've seen before, of course, the concentrations of products increase with time, but the rate at which they increase is slowing down. So when we get to the reaction time of something around 250 seconds out here, and we measure the slope of the NO concentration line, you can't, it's so straight that you can't even see the tangent itself because the blue line itself is virtually a straight line at this point. But the change of concentration with time at that point is 8.6 times 10 to the minus 6, or with the same exponent, about 0.86 times 10 to the minus 5. So the reaction has slowed down to about 1/5 the rate that it was at the very beginning. And if you now compare that to the same point for the O2 curve, and again get the slope here, it turns out to be 4.3 times 10 to the minus 6, which, as it must be, is exactly half the slope of the NO concentration increase, because the two are in a 1-to-1 ratio, and so they must be like that. Now, there's one other point that I'll emphasize on here that we'll talk more about in the next lecture, and that's this vertical line here that I drew in, this red dashed line. This represents the half-life, 190 seconds. The half-life of any reaction, as we'll see next time, is the time it takes for the initial reactant concentration to decrease to half its initial value. In this case, the NO2 started at 0.01 moles per liter, and the time it takes for it to get to 0.005 is 190 seconds, and that's referred to as the half-life. It turns out that the half-life carries some important information for various kinds of reactions that are of a particular kind where the half-life is meaningful. And we'll see more about that when we talk about this next time.